again for the introduction. So my presentation today is pretty much around beam shaping, static, but I mean most of the content is around the dynamic beam shaping for e-mobility applications. Okay, so that will be the main topic for today. So just a bit of introduction about I mean where we are and what we do. So we are in the WMG. WMG is a Warwick manufacturing group within the Warwick University. So I hope you can see the map here on the right-hand side. So we are physically within the Coventry area. So Coventry is within, it's literally the middle of England. So we are within the Automotive UK hub. So we have major car manufacturer co-located not far away. And I mean, one of the largest one, probably the largest one in UK, in England is the Jaguar Land Rover. So we are not far away. So we are very automotive focus. The main focus for us is low carbon mobility. So anything around low carbon mobility. So starting from battery systems, autonomous driving, advanced manufacturing technologies. So everything is really you know, moving around that in terms of research, development, and applications. So the laser welding lab, we have 15 people on board between researchers and student and PhD students. So the team is also, I mean, has been growing over the last couple of years, and is still growing. So which is a positive news. So what we do, yeah, you can see here. So we cover you know, those 5 main areas. So going from the fundamental, so the physics of the laser to the material. So laser to material interaction, then the process modeling and digital twin in general, then sensors, monitoring and control. We work a lot in full-scale prototype for with end users. So end users are very often coming to us and then asking to develop, obviously, together with their input, the pre-production series prototypes that they can test and then, you know, take a decision after that. And this also includes, you know, quite intense testing and characterization. So we can cover pretty much all those 5 areas in-house. And then talking about the TRL level, yeah, this is what I usually show. So we can start from feasibility studies. So eventually understanding, you know, the metallurgy of the material for a given laser input. And then we can go again together with end users all the way up to the TRL 7, which is, you know, like full-scale prototyping together with the testing. So yeah, from fundamental research all the way to full-scale prototype. Probably I'll go very quick on this. So the laser lab, we are very laser welding focused. So the lab has been growing, and you can see here, I mean, some of the equipment we have available now. I don't want to mention, I mean, anything in detail, but you can see some of the, I mean, the laser optics, sensors, and software we also have available for process development. So we have recently installed the C1 laser 14 kilowatts, which, and I will show some results now in the next couple of slides. So now let's come to the, I mean, the main point. So production at scale for e-mobility. So now from our experience of, you know, working in a battery system related welding projects, yeah, pretty much all the end users are asking for those, you know, 5 points. So first is about welding. So novel welding strategies, and these days also becomes quite important the de-welding. So de-welding, it means end of life, or even a repair of the defective module, like a bus bar. And then I mean they are really asking for sustainable strategies, yeah, for enabling welding plus de-welding. So that is an important element. There is a huge demand for new material combinations, especially for mixed materials, steel, copper, aluminum, which probably everybody is aware of. Cost, yeah, cost reduction is always a big kill when it comes to laser technology, because obviously compared to other technology, laser is always more expensive. So there is always let's say, desire to justify the investment. And one way of justifying the investment is through the core benefit of the laser technologies. Yeah, and then need for zero defects, we know that's we are in a, let's say, ideal lab scenario. Yeah, probably we see no defects, but when it comes to real production, there are variations and uncertainty from many places, including surface contaminations. Yeah, and all those, let's say, factors all together are adding defects. And then controlling defects is the whole game these days by combining sensors, AI, and digital solutions. And also, this is something we see more recently. Yeah, people are asking for training, so upskilling, because they are eventually used with more traditional joining processes, not too much with the laser-based manufacturing, and there is a quite high demand now for upskilling the workforce. Now, the reason why, and this again is from our experience, people are a bit of sometimes afraid of using lasers. First is because of the high capex. And this is probably because people are very associating the laser technology to productivity. Yeah. So when we talk about laser, it's about speed. Yeah. So laser is like a fast process by definition. So very often, yeah, we position ourselves on this level. We say, okay, we can use a laser process to maximize productivity, but then we forget about the second benefit of laser, which is the flexibility. Yeah, so laser is a very extremely flexible tool if used in the correct way. And this is where now we see the biggest benefit or the biggest opportunity of the beam shaping, because beam shaping either in time or in space, or time and space together. So we see the biggest opportunity. So obviously beam shaping is nothing new. So technologies for beam shaping has been around for probably more than 15 years by now. But only these days, yeah, because of the latest advancement in scanners and also laser systems, and because of the demand from e-mobility, we see people asking more and more for not only productivity, but also for flexibility. So flexibility for us is the next upcoming requirement from the end users. And this is true especially when we are dealing with low volume and high diversification manufacturing. So it means it's not only one product type, but multiple product types. And this is exactly where the flexibility plays a role. So this is where beam shaping, yeah, again, comes into the picture, and is the motivation for the beam shaping. So why beam shaping in the first place? Probably for three reasons. First, because we can have a more optimized weld profile, or we can control the weld profile. Second, and this is probably where most of the people are focusing their effort these days, is the control of the molten pool and the keyhole dynamics, eventually for reducing porosity and spatters. And then another area which we see of interest is the control of the microstructure. Now, statistically speaking, there is a lot of let's say academic work and industrial implementation between the first two areas, so weld profile and molten pool dynamics. There is very little on using beam shaping for controlling the microstructures. Now, there are some academic contributions. Probably there are some few industrial implementations, but most of the emphasis is around the first two. So now we see and we believe that using the correct beam shaping, we can also influence the microstructure, and that's why we have been investing time and effort in doing that. So now the material, which is very a high demand these days, is aluminum. So 6,000 aluminum for especially for producing the battery cases, so battery trays. Yeah, there are many, design, many architecture where end users, OEMs are using those extrusions, especially extrusions for producing battery casing. So the practical challenge is the weldability of the 6,000. So there is an evergreen challenge, which is the sensitivity to hot cracking. So 6,000 are really not very friendly to be welded with the laser. They become more friendly if we put the filler wire. So then it becomes a hybrid process, laser plus filler wire. But if you do that, you are increasing the complexity. Eventually, you have to reduce the speed. You need more power. You need gas. You need wire. So there is more complexity and more cost overall. So welding with the wire is the the state-of-the-art process today. But industry is eventually aiming, or it's like a wish list, is to go away from wire and then weld fully autogenous. So now this video is clearly showing, a very, nasty crack here opening in the middle of the weld. Is a central line crack. The color map is showing the strain induced by the thermal load, and obviously because of the combination of the thermal load, the chemical composition of the alloy and the microstructure, then you get cracks in the end. So means those welds are not really functional. So how we want to approach it, is using beam shaping, dynamic beam shaping in particular. So we have been testing over the last few months the technology from C1, so the coherent beam combiner with optical phase array. So now, without going into the technical details of the setup, in essence, is a 14 kilowatts total. Although for the materials we have been using, we have used far below around 3 kilowatts. So it's a combination of 0.4 to 0.8, 60, 61 aluminum in overlap. The requirement is a full penetration weld and obviously structural, so no major cracks. So we test a different shape. So this is one set, starting from a standard single core to something more like triangular or arrow-based shape. And then we also tested something more dynamic. And you can see some of the frequencies we have been using. And those are some of the results now. So those are the tensile load in megapascal for those shapes. So now if you compare the baseline on the left-hand side, so close to 80 megapascal, and then you see how much improvement you can get by changing the shape. It's almost 20% improvement only by changing the beam profile. And this is like semi-static because it's only one shape. Then if you add the dynamic element, dynamic element with the, given in this case, we didn't go more than 1000 hertz. You can see again the trend. There is a margin for improvement. So this only suggests one thing in the end, that changing the shape from a, let's say, round axial symmetric Gaussian or close to be Gaussian profile to something else, like a triangular profile, has two main benefits. So first, the possibility of changing the thermal gradient, especially in the lateral direction. And then reducing thermal gradient, eventually you are reducing thermal stresses, and reducing thermal stresses eventually because of the impact on the during solidification on the grain structure, there is better chance that the welds will sustain, let's say, the thermal load and wouldn't crack in the end. And the results are quite evident here. So clear benefits we see in using the beam shaping, but there are also clear challenges. And one of the biggest challenges is to say, okay, great, we have all this flexibility, but flexibility comes with a cost. So first, how do we choose the optimal shape? It can be anything, right? So we can start from a core and ring. We can add a triangle on it. We can add a tail beam behind. So that is a big open question. And to answer this question, we have to understand all the physics behind the relationship or the interaction between the laser and the material, the laser and the molten pool with all the multi-physics and the multi-scale element involved. So the controllability challenge is definitely there, which we must address. So the next challenge is acceptance. So more flexibility means more costs for the end user. And we need a clear business case to justify why more flexible means eventually benefit for the end user. The next is the reconfigurability. That means it's not only the laser process alone, but it's the laser together with the jigging, the clamping, and all the automation around. And then, talking about, the AI and this industry 4.0 kind of logic is the connectivity. So again, it's not like a standalone laser machine, but the machine must be eventually connected. And then we have data collected from the process. And then eventually using AI technology, we can have like a smart system in the end. So we took those 4 challenges on board, and the idea was, right, so what about, rather than thinking about an isolated welding process, we have a laser as a service. A laser as a service understood that the manufacturer will be able to produce parts on demand, and then with a rapid repurposing of existing welding equipment, laser welding equipment. So that was the whole idea we had, or the whole motivation behind one European project, which we have been granted, that is laser for mass. So the whole idea is a laser as a service for enabling digital platform with dynamic beam shaping for supporting, the next generation factory, which is supposed to be smart, decentralized, and sustainable. Now, answering the question, what can you do for us? Yeah, so the project will be having, we are going to have the kickoff of this project in January, so in a few months from now. And we're really looking for partners or industrial or even academic members of the Industrial Advisory Board. We already have few members in the advisory board, but we're looking for more members, especially for those companies or for those institutions that they see the benefits or the opportunity of using the beam shaping for controlling thermal cycling and improving eventual material properties, especially within the logic of laser as a service. Okay, so the logic of rapid repurposing and servitization in general. So with that, I close my presentation. So now if there are any questions, I'm more than happy to take any questions from the audience. Yeah, thank you.